Hi guys, so in this lecture we'll be talking about some exceptions and we'll be talk about the less stability of anti-aromatic compounds. Okay, so let us get started. So we have this exception that when you see this compound you will think that okay, it has um, 8 pi electrons, it is planar, it is cyclic, it is having delocalized pi bond electrons across the compound, so it must be anti-aromatic. But on the contrary, this structure actually has carbon-carbon chain within itself. So actually this structure exists in nature in a tub shape, not a planar compound. It exists as this compound. Okay, it doesn't exist as a planar compound, it exists as a tub shaped compound. Hence it is no longer a planar compound, hence it is a non-aromatic compound, and the name of this compound is annulene, and as it is having 8 carbons, so its name is annulene 8. Okay, so the second point is when you see this compound you will see that okay, it is having 1 2 3 4 5 6 7 8 9 10 pi electrons. It is planar, it is cyclic, it is having this delocalization of pi electrons. It should be okay, 1 2 3 4 5 6 7 8 9 10. So it should be what, I think I have drawn something wrong here. No, I think it's fine only. So it should be aromatic, but on the contrary, you can see that actually we have steric hindrance between these two hydrogen atoms, this and this. So because of that it exists in nature in a twisted form, right? So by twisted form I mean that by darkening this carbon bond I want to show that it is in the towards the face of the observer, and this is actually away from the eyes of the observer. So this is how the compound is formed in a real way, so that the hydrogen bond here and here are separated from each other. Hence it is not a planar compound, that's why it is a non-aromatic instead of aromatic. It is non-aromatic. So these are the two exceptions we face when we actually experimented to find their structure, and the name of this compound is annulene 10. Okay, annulene 10. So please remember the exceptions of annulene 8 and annulene 10. They are both non-aromatic. Okay, so let's talk about some fact here. So just to remember JTR, I call it. So we have something called as inorganic benzene, where the structure is something like this. alternate boron and nitrogen atoms, where boron has negative charge because of its unfilled p orbital, and nitrogen has positive charge which it has donated to boron to form a bond between them. So this is what is called inorganic benzene or borazole. Okay, and resonance actually takes place from bond to bond, double bond conjugation takes place. So this is called inorganic benzene or borazole. Okay, so let us talk about more about the less stable nature of anti-aromatic compounds. Less stability of anti-aromatic compounds. Okay, so anti-aromatic compounds exist in nature in the form of dimers at room temperature. So let's say I have this compound which is anti-aromatic. Why? Because it is having 1 2 3 4 pi electrons, planar sp2 hybridized, so it is planar, cyclic and delocalized with the radical and the it's a conjugation of double bond and free radicals, right? I hope you remember this case when we were studying resonating structures, right? So actually this exists as these free radicals actually combine themselves to form this compound. So this is a dimer. Okay, so anti-aromatic compounds can be easily isolated in inert solvent. So we have some solvent, this is the case, and we have some inert solvent. X implies the presence of inert solvent, and we have some anti-aromatic compound here, just like this. So it will stay just like this in the presence of inert solvent. So this is nothing but inert solvents like nitrogen, argon, something like that. So these type of compounds actually exists only in Pluto. I am talking about the planet. Okay, so exists the anti-aromatic compounds exists only in Pluto, and they can be actually isolated at 4K temperature. Okay, so we'll be talking about resonance energy or conjugation or delocalization or stabilization of organic compounds in the next lecture.